In the previous video, we found a general expression for the initial speed of a horizontally launched projectile in terms of its range and initial height. And that muzzle speed turned out to be r times the square root of g over 2h. And this is a really practical way to measure the muzzle speed of a projectile launcher in the lab. Unfortunately, when we do the uncertainty analysis for the muzzle speed, it turns out that the uncertainty in the launch angle dominates the uncertainty in the muzzle speed. So we can't just pretend the launch is perfectly horizontal. And in fact, for most projectile launchers, a responsible estimate of the uncertainty would be plus or minus 1 degree. So this uncertainty complication forces us to go looking for a more general expression for the muzzle speed as a function of range and angle. And then we'll be able to follow up with a numerical estimate of the uncertainty in launch speed that includes the uncertainty in launch angle. So to get started, we imagine tilting a projectile launcher up at a fixed angle and then firing the projectile at higher and higher speeds. As you can see in the animation, and as your intuition probably already told you, the projectile is going to travel farther as the velocity increases. And because of this monotonic dependence of range on velocity, we should be able to turn this relationship around and use the range of the projectile to determine the muzzle velocity when it was launched. So, like any projectile motion analysis, we begin by looking separately at the horizontal and vertical motions. And before we start out, I want to point out that I placed the origin directly below the point where the ball emerges from the projectile launcher. And this gives us an initial height for the launch that we called h, and then we're going to call the range of the projectile r. So we write down the horizontal equation of motion for the projectile, and that's x equals x naught plus v naught xt. That just says the x velocity is constant. There's no acceleration in that horizontal direction. And then we write down our vertical equation, that's y equals y naught plus v naught yt minus 1/2 gt squared. And in the vertical direction, we do have an acceleration, and that acceleration, as usual, is negative g. So then we plug in the stuff we know about the horizontal motion. And there we've plugged in a final value of r for the x-coordinate. The initial value was 0 because I placed my origin directly below that initial location of the projectile when the flight began. And then our x component of the initial velocity is v naught times cosine theta. That's the horizontal component of that initial velocity. Now it's going to be useful to solve this for t. T is the flight time here. And we get this expression, t equals r over v naught cosine theta. So then we plug in everything we know about the flight into the vertical equation. And there I see that the final value of y is 0. And that's because the ball hit the floor and the origin was placed at the floor level. The initial y value was h. The initial y velocity was v naught sine theta. That's the vertical component of that velocity vector. And then, of course, we have our acceleration term where I can see an acceleration of negative g for this thing. Now, the flight time of this projectile is not what we're interested in, and that's actually why I solved for it in the horizontal equation. And what we're going to do here is take that flight time expression, r over v naught cosine theta, and then we're going to sub it in everywhere we see a t in the vertical equation. So making that substitution, we arrive at this rather large equation, 0 equals h plus v naught sine theta times r over v naught cosine theta, minus 1/2 g times the quantity r over v naught cosine theta all squared. That's just replacing all the t's with r over v naught cosine theta. But things are going to clean up a little bit. I can see that the v naughts are going to cancel out of that second term. And I have a sine theta over cosine theta, which I could rewrite as a tangent. At the same time, I'm going to clean up this last term by squaring the top and bottom of that fraction, and then gathering all the terms into a single fraction. All right, so now we've re-expressed it this way. We have 0 equals h plus r tangent theta minus gr squared over 2v naught squared cosine squared theta. Now remember, the goal here is to solve for the initial speed v naught. And that term is hiding in the denominator of that fraction at the end of our equation. So the next move I'm going to make is to add that fraction to both sides of the equation. And the point here is to get rid of the minus sign and to make some progress in isolating that v naught squared. Okay, so now it looks like this. Gr squared over 2v naught squared cosine squared theta is equal to h plus r tangent theta. And we're trying to isolate that v naught squared. So what I'm going to do is multiply both sides by v naught squared to move that guy to the right side of the equation. And at the same time, I'll divide by h plus r tangent theta, putting that into the denominator on the left side. So that gets us here, and we're getting really close to having v naught isolated now. On the left side, I have gr squared over 2 cosine squared theta times the quantity h plus r tangent theta. And on the right side is just a v0 squared. So all I have to do now is take the square root of both sides, and I've solved for v0. And there's my final expression for the muzzle speed of this projectile launcher, v0. It turns out to be the square root of gr squared over 2 cosine squared theta times the quantity h plus r tangent theta. So now we know how the muzzle velocity depends not only on the range, but also on the launch angle of the projectile launcher. And we should at this point verify that we retrieve the formula for the muzzle speed of a horizontal launch when we plug in an angle of 0. So checking that real quick, we plug in theta equals 0. And notice, because the cosine of 0 is 1, that term is going to vanish in the denominator. And then the tangent of 0 is 0, so the r tangent theta term is gone. That means in the denominator, all that survives is a 2h. And at the same time, I'm going to factor out the r squared out of that square root. That becomes an r outside of the square root. And we arrive at this familiar expression for the muzzle speed of a horizontally launched projectile. That's just r times the square root of g over 2h, the same expression we derived in the last video. In the next video, we're going to get the payoff for all of this work, because now that we know how the calculated muzzle velocity depends on launch angle, we can proceed with the propagation of error analysis and put some responsible error bars on v0. I'll post a link to that video at the upper left when it's done, and I'll see you there.